Hi, in this module I will discuss constitutive equations. Constitutive equations are the relations between stresses and strains. We have seen that when loads are applied on the body, then internal forces are developed inside the body and there are deformations inside the body. We have defined internal forces in terms of stresses and deformations in terms of strains. Now we want to establish the relationship between stresses and strains. The relationship between stresses and strains depends on material behavior. These material behavior equations are called as constitutive equations. The relationship between stresses and strain are called constitutive equations or material model equations. There are many types of material model equations depending on the assumptions taken in respect to material behavior. The simplest material model or constitutive equation is linearly elastic isotropic model. This material model is called as Hooke's law. The examples of other material model or constitutive equations are viscoelastic model, for example, as in the case of fluids, elastic orthotropic model, and there are many other examples. But in our study, we will be using only Hooke's law, that is valid only if we assume the material to be linearly elastic and isotropic. So before going ahead, I will discuss certain terminologies that will be used frequently in this chapter. The first one is elastic material. A material is said to be elastic if it returns to original shape and size when loads are removed. Consider this body on which axial loads are applied, due to which this body will elongate in this manner. Upon removal of load from this body, if the body again regains its original shape and size like this, then we call this body as an elastic body. Elasticity of a material is determined by two material constants, namely modulus and elastic limit. So let us first understand modulus. Modulus is the ratio of stress to strain. That is, it is the amount of stress needed for a particular strain. We define modulus as the ratio of stress to strain. We can understand it like stress needed for a particular strain. If more stress is needed for a particular strain, we say that the material has large value of modulus. Therefore, those materials that have large values of modulus will have less strains, and therefore such materials will not deform easily. That is, the higher the modulus, it means harder to deform the material. There are different moduluses. The first one is the modulus of elasticity, denoted by E. It is also called as Young's modulus of elasticity. It is defined as the ratio of direct stress or normal stress to direct strain or normal strain. That is, Young's modulus E is equal to normal stress sigma divided by normal strain epsilon. The second one is the modulus of rigidity, denoted by G. It is also called as shear modulus. It is the ratio of shear stress to shear strain. That is, G is equal to shear stress to shear strain ratio. The third one is the bulk modulus, denoted by K. Bulk modulus is the ratio of direct stress to volumetric strain. That is, K is defined as the ratio of direct stress to volumetric strain. Volumetric strain, denoted by epsilon V, is the change in volume divided by original volume. So these three moduli will be used frequently. Now elastic limit is the stress beyond which the material no longer behaves elastic. After elastic limit is reached and the material is further deformed, then it will not return to its original shape and size. That is, after the elastic limit is crossed, it is said that material has entered to plastic region. But we will limit our study in strength of materials to elastic limit only. Linearly elastic material. If the stress-strain relationship of a material is linear, the material is said to be linearly elastic. This linear elastic material is an assumption that is taken to simplify the relation between stresses and strains at a point, because the linear relations between two quantities is the simplest relation. Isotropic material. A material is said to be isotropic if its properties do not vary with direction at a point. So, an isotropic material has same values of a material constants in all directions at a point. When I talk of isotropic, it simply means that at a point the material properties are equal in this direction, this direction, this direction, in any direction at this point. So isotropy is always to be observed at a point only in different directions. Poisson's ratio. It is defined as the ratio of lateral strain to longitudinal strain. That is, nu is the ratio of lateral strain to longitudinal strain, and a minus is also put to make nu values positive. Consider this body on which axial load P is applied. It is observed that due to this axial load P, this body not only elongates in the x direction but also reduces along the diameter. So the new diameter is d dash and the original diameter is d. The original length is L. Therefore, we can write Poisson's ratio here as lateral strain, that is strain in the diameter, that is strain perpendicular to the longitudinal axis, which is d dash minus d whole divided by d, to the longitudinal strain, which is L dash minus L divided by L. Since d dash is less than d, therefore the term d dash minus d will come negative, and this negative will make nu as positive. It is to be noted that Poisson's ratio is a property of material and it is not dependent on the load applied P. Now we can write the Hooke's law, which is valid only for linearly elastic isotropic material model. We have learned that at a point there are 6 independent strain components and 6 independent stress components. Without any additional assumptions, the relationship between these strain and stress components for a linearly elastic material can be written like this. In this relation, the relationship between 6 strain components and 6 stress components is established. These constants are called as material constants because the relationship between strain and stress depends on material behavior. It can be seen that to establish the complete relationship between 6 strain components and 6 stress components, we need total 36 material constants. Therefore, 36 material constants are needed to describe the linear relationship between stresses and strains. It can be seen that this strain is related only linearly with the stress component, that is, it is raised to the power 1. So this linear relationship requires 36 material constant. However, out of 36, some constants can be proved to be equal. Therefore, there are only 21 independent constants for a linear relationship between stresses and strains. So, out of 36, if we know 21, then we can find the rest. So, there are only 21 independent constants. Now, if we additionally assume that material is isotropic also, then the number of independent constants reduces only to 2. That is, if we have assumed that our material is linearly elastic as well as isotropic, then we need only 2 independent material constants to relate stresses and strains at a point. That is, in this general linear relationship between stresses and strains, the constants C4, C5 and C6 will become 0. That is, normal strain epsilon xx is dependent only on normal stresses sigma xx, sigma yy and sigma zz, and do not depend on tau xy, tau yz and tau zx. Therefore, C4, C5, C6 becomes 0. So we can eliminate them. Similarly, normal strain epsilon yy depends only on normal stresses and do not depend on shear stresses. Therefore, C10, C11, C12 becomes 0. Similarly, epsilon zz depends only on normal stress components and do not depend on shear stresses components. That is, for a linearly elastic and isotropic material, the normal strains depends only on normal stresses and not on shear stresses. Therefore, 16, 17 and 18 will also become 0. Shear strain also will depend only on shear stresses and not on normal stresses for a linearly elastic isotropic material. Therefore, C19, C20 and C21 also becomes 0. Also, it is found that gamma xy depends only on tau xy and do not depend on tau yz and tau zx for a linearly elastic isotropic model. So, C23 and C24 becomes 0. Similarly, gamma yz will depend only on tau yz and not on any normal stress component and other shear stresses component. Therefore, C25, C26, C27, C28 and C30 will become 0. On the same ground, shear strain gamma zx depends only on tau zx. So rest all material constants will be 0. Therefore, finally we get gamma xy is equal to C22 tau xy, gamma yz is tau yz into C29 and gamma zx equal to C36 zx. Now these material constants C22, C29 and C36 are all found to be equal and equal to 1 upon g. Therefore, we get gamma xy is equal to tau xy by g. Similarly, gamma yz and gamma zx. Now for normal strains, epsilon xx, C1 is found to be 1 upon E and C2 and C3 are found to be equal to minus nu by E. Similarly, C8 is found to be 1 upon E and C7 and C9 are found to be equal to minus epsilon by E, and C15 is 1 upon E, and C13 and C14 are equal to minus nu upon E. Therefore, the stress-strain relationship for a linearly elastic isotropic material model, that is Hooke's law, can be written in this manner, where epsilon xx is sigma xx minus mu sigma yy plus sigma zz by E. And like this, we can also write for epsilon yy and epsilon zz. Similarly, gamma xy is tau xy by g, gamma yz is tau yz by g, and gamma zx is tau zx by g. These 6 set of equations are called as generalized Hooke's law, and they are valid only for linearly elastic and isotropic model. Now we can also write Hooke's law for principal stresses and principal strains. We have found that the normal strain epsilon xx can be written as sigma xx minus the stresses in two perpendicular directions. We have learned that at a point the principal stresses sigma 1 and sigma 2 are perpendicular to each other. Consider a plane state of stress at a point. So sigma 3 will be equal to 0. Therefore, we can write epsilon 1 instead of xx. So we have to write here sigma 1 instead of xx. We have to write sigma 1, and sigma y, that is perpendicular to x, is to be written as sigma 2, because sigma 2 is perpendicular to sigma 1, and sigma zz is sigma 3, which is 0. Therefore, we get epsilon 1 as sigma 1 minus mu sigma 2 by epsilon. Similarly, epsilon 2 can be written as sigma 2 minus mu sigma 1 by epsilon. So this is Hooke's law for principal stresses and principal strains. Now these elastic moduli we have seen, that is E, G and K, are related by this relation. E is equal to 2G 1 plus nu. The second relation is E equal to 3K into 1 minus 2 mu, and the third one is E is equal to 9kg upon 3k plus g. So if any of the two quantities, that is either E, G or nu, is given, then we can find the third one using these relations. Now let us find the range of Poisson's ratio. We have seen that E is equal to 2G 1 plus nu. Now since E is a material property, Young's modulus, and G is also a shear modulus, therefore E and G are positive, because E is defined as the ratio of direct stress to direct strain. This is positive, this is positive, so we get Young's modulus E as positive. Similarly, G is always positive, therefore 1 plus nu should also be always positive. Therefore, we get that nu should always be greater than minus 1. We have also learned that E is equal to 3k 1 minus 2 nu. Therefore, since E and K are positive, therefore 1 minus 2 nu should always be greater than 0. Therefore, 1 should be greater than 2 nu, and nu should always be less than 1 by 2. So from these two equations, that is this equation and this equation, we get that nu lies between minus 1 to 1 by 2. This is a theoretical relationship. For metals, nu is always positive. This ends this module. Thank you.